Hey guys, welcome to the third episode of AbhiramLabs podcast. Now, I want to make this podcast a bit different than other podcasts. We're not going to discuss anything about the AI topics or on our journey, and we are not joined by Kripun Kumar sir today. I first want to explain and help you understand LLMs so that you can make some sense of it, because that's really important, as LLMs are turning the world completely upside down with their results from ChatGPT to Bird to Bing or to Anthropic's Claude. All these models are LLMs. So let's first try to understand what LLMs are and why they are so significant in this AI transformation that we will see in the couple of following years or maybe more. Okay. Now, the first thing, LLM stand for large language models. So when you say language models, these models typically handle languages like natural language, and they can generate text, they can classify the text, they can do many different things on this text, number of tasks. And all this comes to natural language processing, the NLP tasks. Okay. Now, at the core of a LLM, we have transformer layers. Now, LLMs are typically built on hundreds of transformer layers, and the transformer layers are a bit different from other natural language processing models. Transformer layers are a type of deep learning models which have been crucial for NLP from the past few years. Now, what they do is they track the relationships between different tokens or different words in a sequential data and use that to generate more data, or to classify this data, or to classify those tokens, and to do different NLP tasks. And to do this, the transformers use something called as an attention. Now, before we go ahead and understand attention, let me first tell you, why do we need these transformers, right? Now, before transformers, the most SOTA models, which are the state-of-the-art models of NLPs, were RNNs, which is recurrent neural networks. They're basically a sequence of neural networking layers that can handle the data, handle the textual data, and do the same task. But they had many issues. They had many things that they were not doing right. The first thing is, the models were typically built to handle sequential data, but when you have a large sequence of data, parallelization can really help. And the RNNs couldn't do that because they were inherently built to handle, and the combinations of RNNs works in a sequence, like a single word is passed in the model at a time, or in a group of few words. And this also led to the problem of missing dependencies between large text. So now let's assume we have a large sentence, and if we want to find the dependency between the first and the last word of the sentence, it will be really hard for RNNs to do that, because they would need large amount of compute to do that, as they don't support parallelization, and they need a large amount of memory to eventually get to the last word of a sentence and to be able to find the dependencies between these two. To address that, this is after years of development have found something called an attention mechanism. Now, attention mechanism is the core part of transformer models. What attention mechanism does is, it focuses only on the relevant part of the input text. It has found a way to figure out which part of a sentence is more important for that particular output task or output query. Now, the mechanism gives some weights to each token of a sequence, and these weights will tell you which part of the sentence should we really focus on. So the model mostly focus on to be able to generate a good output. Now, attention mechanisms are really hard to explain if you don't have any pre-context on this NLP tasks or without some neat infographics. Mechanisms allow the model to focus only on the relevant part of a sequence of data based upon the output query. When I say output query, it can be like filling blanks in a word or translating it into different language. Now, the attention mechanism gives weights to each token of a sequence of input data, and these weights will tell you how relevant it is. These weights can be based upon a single sentence with the intra-sentence or even inter-sentence, even between different sentences. Now, this kind of context of relevancy being introduced into these models has really helped the transformers to dominate the NLP paradigm. So now it's really hard to explain attention mechanisms without prior knowledge and without neat infographics. So I would recommend you to check out a video by my fellow YouTuber Michael Fee, which has this neat infographics that clearly explains the whole transformer model with each step. Now, what's the benefit of attention? So when you use the attention mechanism, the first thing is you can do the tasks in parallel. Okay, because you are trying to find relevancy of a word in a sentence, it doesn't need to be in a sequence. So you can have these parallel attention layers that can work each on different words, and they can all work parallelly. It allows long range dependencies between tokens which are far apart in a sentence or even a group of sentences. And it also reduces the complexity of RNNs by a great degree. RNNs are really these complex architectures, but transformer layers are just generally matmals between these different components of the attention layers. Now, when the researchers discovered the attention layers and figured out that these can be really helpful, the first thing they did is they added these to the RNNs, because that's typical what you want to do. When you create something new that seems to be helpful, you put it into something that you already know is good but has some problems. But in 2017, a paper published by Google Research has proved that if you remove all the RNN layers and use only the transformer layers, that can improve the results even better. This paper titled "Attention is All You Need" is a landmark for what we have seen so far in LLMs. So now that was, I think, the first paper introducing transformer model only using attention mechanisms. And they have shown that these results in a few translation problems have exceeded other sort of either RNN models or the combination of RNN and attention mechanisms. And at the same time, when OpenAI was developing its own GPT versions, they picked up this and put this into GPT-2, which was, I think, the first, you can say, I don't know if you can say large language model, but it's surely a language model. So with GPT-2, they have seen that this attention mechanism has a potential to do few short learning. Now, typically, before we had this LLMs and everything, when we use only CNNs or RNNs for different tasks in deep learning, the models can only perform well in supervised settings. That means when you ask it to do a specific task on a certain amount of data which it has been trained on, only then it can do well. If you train a model on dog images, it can classify dogs. If you train a model on cat images, it can classify cats. Now, there are a few cases like these large models like ResNet, or which when you train them on large context of data, they can do some simple tasks on different kinds of data. But even the tasks are still localized to the way they are trained on. Like if you train a model to segment, it can only work but good on segment. If you train a model to classify images, it can only work on classifying images. Now, feature learning is the capability of a model to infer a certain type of specific data set if that's included in a small percentage in the training data. Now, before the introduction of attention mechanisms, people and researchers thought that these models can only work in a supervised fashion. Now, supervised fashion, especially in NLP tasks, means that if a model is trained on a certain data set, it can only work well on that particular data. If you ask it to do a task, a different task, or maybe the same task on a different data, it might not achieve the performance that it did with the data it's trained on. Now, people have realized that using attention mechanism, using transformers, the models can do few shot learning. What's few shot learning? Few shot learning is the ability of a model to learn a specific type of data if it's included in a small percentage the training data. Now, let's assume that if 5% of the training data is about vegetables, then the model can achieve comparable performance on classifying or creating recipes using these vegetable data that has been trained on. This capability would really transform the AI. Now, these capabilities mean that you don't need large data which compiles all the information for the model to work on the different data sets or different types of data. Now, GPT-2 was built on this concept that these models can do few shot learning, and the few shot learning capabilities can be really helpful for us. But the problem was with GPT-2 and other models at that time, it was hard for these models to create dialogues or to talk or to chat like humans. They seemed so robotic and mechanical. They weren't able to understand, even though if they were trained on data which is mostly from internet and other social media platforms like Reddit and Twitter, they weren't able to imitate humans. Now that's when OpenAI introduced RLHF, which is reinforcement learning with human feedback. Now first, let's understand what reinforcement learning is. Now reinforcement learning is a different problem than typical supervised machine learning or deep learning, where the model does something in a trial and error fashion and learns it that way. Well, let's take an example of a car, self-driving car. Now, any of these cars, like all these like companies like Tesla and Uber and Comma and all these car self-driving companies have some simulations where the car tries to navigate in a world model. And here it's not typical like deep learning where you show it thousands of videos of humans driving and it can drive after looking into that. It need to drive first to understand how the controls and how the kind of the physics works, and then to fail and to learn from that. They create a reward function that will teach the model how not to fail every time after it fails. And this will take like thousands of runs until it learns some basic things like maybe driving straight on the road or taking a left turn. And this repeat for many days and many years until the model becomes sufficiently good enough to be added to a car. Okay. Now, reinforcement learning with human feedback is something different that's been introduced by, I think, OpenAI. After the model has been pre-trained on a large corpus of data, our data from social media platforms, it is trained in a reinforcement learning fashion where it receives feedback from humans depending upon the results. Now, because real RLHF mostly works with dialogue, let's assume that the model is being asked to talk to a human. Now, the input would be the prompt which we give to like ChatGPT, maybe like "Hi, how are you?" or something like that, and the reply can be maybe 2 or 3 options, out of which the human selects one and tells the model that this is how it's supposed to reply because that's how humans speak. And the whole goal of RLHF is to teach the model to talk like a human by getting feedback from actual humans. That's how these models know when to reply an answer, when not to. Like if you ask ChatGPT to help you build a time bomb, it would clearly say no. And this is trained with RLHF. So the model it's not something like the data is being captured by the OpenAI's APIs, and that's not how it works. It actually goes to the model, and the model is able to understand that when these kind of questions are asked, how a human would respond to that, and it will learn that from the RLHF concept, where most of these harmful, any controversial or any racist remarks have been kind of flagged when the humans give a negative feedback for these kind of replies. That's how these models are trained, and that's how these models know when not to give a actual answer like they're supposed to do. Okay. Now RLHF seems to be doing its work, because whatever we have seen so far, ChatGPT 3.5 and the later version of GPT-4, and also all the other models, they all seem to talk like a human and make it at least believe in some sense that we're talking to when maybe a child or maybe a small kid, is due to the RLHF concept. That's been critical. But it has many fallacies. Okay, RLHF, I mean, they're not sure. Right now it works fine, but experts believe that it would fail if we go any further. And it also has many problems, like the first thing is you need to be really careful about the people who give the feedback, because they represent the entirety of human to the model, right? Now you can't, it's really hard to put an entire context of the whole world, because we are so diverse, into one or a group of humans. And OpenAI needs to, and all these companies needs to be really careful of putting the right people that represent the world. You just don't want people from just some class, because that would be again biased, right? So it's really hard for them to do that. And even then, I think it's hard for any group of people, no matter how many tests you put them on, how much you try to train them, for them to completely represent an entire population of humans. And there are different issues like that, but so far it's been working really great. So I don't have any problems with that. So far it's been working great, so we don't need to be worried about that. Now this is the history of LLMs, right? From attention to transformers to LLMs to RLHF. That's where we are right now. Okay. Now we don't know what GPT-4 has. You may believe that it's just a larger model of GPT 3.5, but I wouldn't, because if that's the case, OpenAI would have released at least some information on the model. The very fact that they have not given out any kind of information about the model implies that they have something to hide, maybe different architecture, maybe different reward function, maybe different training process, not sure. But it's GPT-4, there's quite a significant difference between GPT 3.5 and GPT-4, and that especially is in these nuances, right? When there's a way to behave like human. For example, if I ask you to help me with something that you don't want to, you don't just straight up say, I don't want to do that. You don't do that. Okay, now assume if I ask you to help me with something that you don't want to do, you don't just straight up deny, but you kind of create this kind of sentences and tell me something that seems like I shouldn't ask you any further because you were uncomfortable with that. I mean, it creates this kind of nuances between the way you normally speak and the way you're speaking right now. That helps me understand that this is not the right thing to do. And GPT-4 can do that. When you ask it a question that it shouldn't be answering, maybe in a harmful context or maybe in a racist context, it doesn't directly say no to that. It implies that what you are trying to do may not be good for you or other people, and that it's better to not reply. Like, I think it's better to try yourself. You just go to GPT-4 and ask it to maybe help you build a time bomb. You will understand the nuances I'm talking about, right? Now this is the whole history of the LLMs, and why we are talking about LLMs, because that's where I think we are right now. That's the most advanced AI, where it can kind of talk like humans, and some people even believe that it can think like humans. I'm not sure about that, because when you train something with RLHF, you don't know if it's imitating you actually or if it's trying to fool you by acting like it's imitating you, but its actual reward function is a bit different than that. Maybe that might be the case. Maybe I'm speculating, but we never know. We will only know when OpenAI releases GPT-4 and we get the chance to look inside it and make some educated guesses. But until then, we never know. So LLMs are the closest thing to what you call an AGI, which is artificial general intelligence. Now, AGI is actually should be AI, but people have been using AI so freely that we actually believe that we already have that, but we don't. AI actually, when you say intelligence, it means that it should be able to do things with zero-shot learning. It should be able to adapt to new tasks that it has never known before with just simple few steps and be able to do that just like humans, just like how we do, just like how we learn to drive or we do anything else. And I don't think this is not still AI. You can just call it machine learning if you want, or deep learning or anything, but it's not still AI. But because people have been using it so frequently, we have to come up with a new term called AGI, which actually means the artificial general intelligence. And that's something we believe can be achieved after a few iterations of GPT-4. Maybe we don't know how many years or how many decades it would take, but I think GPT-4 would be in the books of history after maybe centuries or maybe a few decades, where people look back and say, like how we look back and say that this is one of the first earliest computers in 1960 or something, within this large CPUs with filling up the whole room. I think that's how we will talk about GPT-4 in our grandkids or even after their kids talk about GPT-4 when they actually have an AGI. If we are alive till then. Otherwise, we're not sure. Maybe the aliens will have their own books where they will talk about GPT-4. Okay. Now, I think this episode has helped you in some way understand the whole context of LLMs and why we need to learn more about that after each new page, after each new model, because they are at the precipice of a coexistence between AI and humans. And I can't wait for that. I'm going to stop here. I will see you next week. Thank you. Until then, goodbye.